Very much for the invitation to speak. I'm very happy to be here. My first time on this continent, first time in this hemisphere. So far so good, I have to say. What I'm going to talk to you about today is a pair of conjectures, used to be just a single conjecture, in an area of mathematics that to most people seems a little bit esoteric. And the main reason I'm talking about it is not because the topic will be of intrinsic interest to you, of course it should be, but rather because of the methodology that went into its resolution. Okay, so first of all, let me start by dedicating my talk, as I often do, to Bill McCune, the late Bill McCune, who was the developer of the tools that I principally use in a lot of the mathematics that I do, especially Prover 9, which is an automated theorem prover. Bill is probably best known for his work in the late 90s in solving the so-called Robbins problem in Boolean algebra, which was an axiomatization problem for Boolean algebras. And he used automated deduction tools that he developed to solve this. It was one of the first such solutions that there was. Okay, so here are my co-authors who are entirely responsible for any mistakes that I make in the talk. I am not responsible. So my colleague, Petr Wojciechowski, and Bob Viroff, who is a computer scientist at the University of New Mexico. Okay, so the talk will be in various parts. I'm not one of those persons who puts up a slide that shows you the table of contents. You'll just be surprised at what the parts are. So let's start with a little bit about loops, and along the way, I'll sprinkle in some Prover 9 code so that you can see what's going on. And so here is the picture of mathematical science classification area 20. Which is, for most people, the group theory classification. And if you're going to generalize groups, there are generally two directions you can go. The one that people in this room tend to be the most familiar with is the direction on the left. In fact, I would say most mathematicians are more familiar with that one, where you keep associativity, but you drop conditions like the existence of inverses and such things, okay? And that leads you to semigroups and monoids. But there is a different option, which is you keep structure that is related to having inverses, except I have to say that a little more precisely, but you drop associativity. And that leads you to quasigroups and loops. And then if you throw everything away, you're just in the realm of general sets with a binary operation, and good luck. So today we're going to go up the right-hand side of this picture. I'm not going to talk about quasigroups in general, just to keep things a little more focused. I'm going to talk specifically about loops. So what is a loop? So here's what's usually called the combinatorial definition. A loop is a set, it's got a binary operation, and here's the stipulations. For each pair of elements, the equations a times x equals b and y times a equals b have unique solutions, okay? So you can uniquely solve on the left or uniquely solve on the right. And in addition, what makes it a loop, so if I just left off that second item on in the itemized list there, if I left off the second one, that would be the definition of a quasigroup. But I want there to be an identity element. And so we also include that stipulation, and that's what makes it a loop, okay? So, of course, this includes groups. Proving that property there is one of the very first things you do in an abstract algebra class after the notion of group has been introduced. But there are lots of non-associative loops. Let's start with a very simple example, a very small example. In fact, one of the smallest examples. So if you have a finite loop, one thing that what characterizes it is that its multiplication table is precisely a reduced Latin square. Reduced in the Latin square context just means that the first row and the first column correspond to the identity element. Okay, that's the word reduced in Latin square jargon. Okay, now I claim that this is a non-associative loop, this particular one. Can you see why without even working, doing any calculations? Why, yes, James. Yeah, it has a substructure of order 2 in the upper left corner, but it has order 5. So that means that this particular structure violates Lagrange's theorem, so it cannot possibly be associative. Okay. That's a much nicer argument than verifying some or showing that some instance of associativity tends to fail. Okay, but of course we don't want to just play games with Latin squares. So are there loops coming from other settings that are natural? And the answer is yes. Loops actually arise all over the place. So here are some examples. Now, the theory I'm going to be discussing later in the talk is not related to any of these particular examples, but this is just to give you an idea that loops do really show up in real mathematics. Probably the best known example comes from the octonions. If you take the octonions and you throw away the origin, then, so remember the octonions are a non-associative division algebra. So if you throw away the origin, what's left is actually a loop. And in particular, the 7-dimensional sphere, which you can think of as being everything of norm 1, is a subloop of that structure, a non-associative subloop. Another one comes from special relativity. If you take the space of relativistic velocity vectors, so vectors that are of length less than the speed of light, and you apply to them Einstein's velocity addition law, which I'm not going to write down as a formula because it doesn't help with the understanding of how it works. It turns out that is not an associative operation, especially if your 2 velocity vectors were not parallel, or your 3 rather are not parallel. Then that's actually another type of loop. If you take the polar decomposition of real invertible matrices, that gives you yet another one on sets of positive definite symmetric matrices. And there are many other such examples. So loops actually do arise in various parts of mathematics for various reasons. Okay, now loops have also a different description of them, which is sometimes called the universal algebra description, which is the following. So let's say we have one, and we introduce some notation for the unique solution, okay, to the unique solutions, rather, to the 2 equations, okay? So we use division operations, left division and right division, to denote the unique solutions of the corresponding equations. Then there are some identities that necessarily hold, namely that, for example, A divided into AB recovers B, A times A divided into B is B, and so on, okay? So it's actually beneficial to think of loops not as just having a single binary operation, but as actually having 3. The multiplication, a division on the left, and a division on the right, and then satisfying these particular identities. And that may seem like a minor point, but that actually has some computational advantage. It's much easier to encode facts about loops if you look at it from this point of view, as a set with 3 binary operations. And I'll show you what I mean in just a moment. So here, for example, is a typical fragment of a Prover9 input file, where this is just a fragment of a larger one, where here are the loop axioms. And you notice that this is, except for the fact that maybe some of you don't like the Courier font, this is pretty much exactly what I just showed you on the previous slide. It's quite readable, and by the way, this is one of the advantages of Prover9 among other automated theorem provers for beginners, is that you can read it without any background. Okay. What I'm not going to do is give you formal definitions of a lot of the concepts that arise in loop theory that sound like corresponding concepts from groups. And the reason is because the definitions are exactly what you expect them to be. Okay, so for instance, what should a subloop be? Okay, well, you can guess a subset that's closed under the loop structure and so on. Okay. So subloops, homomorphisms, normal subloops, and so on. That's the normal subloops is the only one where it might be a little non-obvious what the definition should be. But if you think about it just in terms of kernel of a homomorphism, then you're fine. That gives you exactly what you want. Quotients and so on. This is basically all stuff that coming from really from universal algebra and realized in this particular setting. Now, there are some notions that are specific to loop theory, meaning that they have no analog in group theory. And let me show you a couple of examples of that. So let's talk for a moment about the center. So here's the definition of the center of a group, okay? The set of all elements that commute with everything, all right? So you might guess, just naively, that this would be the correct definition of the center for a loop. And you could certainly write it down and call it center if you wanted to. But in a sense, it is the wrong definition for various reasons, not the least of which is that this particular set is very rarely a subloop, okay? Except in very special circumstances. Okay? In fact, that might surprise you because you would think that commutativity is a very strong condition, and surely things that are commutative are nicer than things that are not commutative. That's certainly something I think that we're all brought up sort of ingrained into us as mathematicians. That's true in the presence of associativity. But if you're not in the presence of associativity, commutativity is actually not that necessarily a very strong property. And we'll see more about that later in the talk. Okay, so what's the right definition? Well, here's an example of some concepts that have no analog in group theory because in groups they're completely trivial. We lack associativity in loops in general. So that would suggest that the elements that do associate with everything else in the loop might be very interesting, and they are. They are elements of what are called the nuclei, and they have different names depending on where you put the element in the associative law, on the left, in the middle, or on the right. Okay. And then, and you don't need to remember the distinction between the three for this talk. That's not that important. What is important is the intersection of all of them, which is just called the nucleus with no adjective in front of it. And that is always a subloop. It isn't necessarily normal. And it's the set of all elements that associate with everything in any position. Okay. Well, here then is what we consider to be the correct definition of a center for a variety of reasons that I won't go into. The center of a loop is all the elements that commute and associate with all other elements of a loop. Okay, so it's the intersection of the nucleus with that set that I showed you 2 slides ago. Now, this turns out is always a normal subloop and can be characterized in many useful ways. For a variety of reasons, it is the correct notion of center. It agrees, for example, with the very abstract notion of center that is used in universal algebra and so on.
Can I ask a question?
Mm-hmm.
Sorry, online. So it contains the
yes.
identity. Is that clear that it contains the identity?
I'm sorry, one more time?
Does it contain the identity?
Yes, it does. The identity commutes and associates with everything.
Right. Okay.
So, okay. So here's another example of some more input. So let's say that you were working with some special element and you wanted to specify axiomatically to prover 9 that it's in the center. Well, you would literally just type what I said. Okay, here it is. So C is the special element. all automated theorem provers have some convention about what are variables and what are constants. Prover 9's convention is that variables start with lowercase x, y, z, u, w, and then v's. And constants are anything starting with any other letter of the alphabet. So here's, for example, something specifying that some special element C is in the center. It commutes with everything and it associates with everything. Okay. Now, as you may recall from group theory, one of the most useful gadgets in group theory when you're talking about measuring the failure of a group to be commutative is the so-called commutator, which is this expression which is chosen mostly by convention that measures the existence of these things, measures how non-commutative a group is. Okay. You can play the exact same game in loops, and there are reasons to do so. So you can introduce a commutator. Now, this is a convention for what they should be. There are other possible conventions that one could use. And this particular term, so yx divided into xy, is what we're going to consider to be a commutator. But now we are in the non-associative world, so we also want to measure non-associativity. So here is a gadget that has no analog in group theory, namely an associator. Okay, we use the same convention using left division just because that's what everybody does. There's no special reason to use it. To define a term and that term being equal to the identity element or not, so it tells you whether the three elements that are plugged into it associate or don't. Okay? Commutators and associators are very useful. And you can use them as defined functions in Prover 9 or any automated theorem prover. In general, automated theorem provers will work well with defined functions as long as you specify to the prover that you would like it to actually use your defined functions when it does a search, as opposed to just expand them away and forget them. Okay. Of course, if you have a commutator, you're doing a calculation and you immediately get rid of all your commutators and just write x inverse y inverse xy in a group, that's kind of useless. Why did you have a commutator at all? Okay. So here is, for example, some input showing commutators and associators. Now, I get asked this all the time. Why does the commutator an uppercase K and associator is a lowercase a? And the answer is, I don't remember. The K is, of course, the first letter in the word commutator, so that makes perfect sense. But I don't remember why there's this case difference. These definitions were actually due to not to one of my co-authors, but to somebody else, and I just been using them the whole time. Okay, so let's talk a little bit about something that is part of the theme of what I'm going to be saying here, which is how to do first-order encoding of high-level mathematics. Okay, so here are a couple of examples of this. Let's say, for example, that your high-level concept is that you have a loop, and the quotient of that loop by its center is a commutative loop. Okay. Now, that sounds all very high level because, for example, I mentioned quotients, and that's a second-order concept right there. But here's how you would exactly specify that equationally. Okay. What those first four equations say is that every commutator commutes with everything and associates with everything. Okay. So that means that every commutator is in the center. So when you mod out the center, all the commutators will vanish. Another example would be the reason I'm picking, by the way, on these two examples is they're going to come up later. The quotient by the center is associative, is a group. Okay, well, it's the same idea. The four equations on the bottom of this slide say every associator commutes with everything, every associator associates with everything. Therefore, every associator is in the center. Modding out the center means all the associators are equal to 1, and so you have a group. Okay. This idea of taking high-level stuff and writing it in a first-order way is something that really pervades a lot of work with prover 9 in general and, well, prover 9 and automated theorem provers in general. Okay, getting back to some loop theory. There's a useful gadget, which I'm not actually going to be using much other than just to define the thing that comes immediately after it, which is called the multiplication group. Now, the idea is the following. Just as in groups and other settings, you can define mappings for each corresponding element, which are given by multiplication by that fixed element on either one side or the other, the left or the right. Now, in a loop, or even more generally a quasigroup, those maps are actually bijections. And that's actually by definition of loop. That's actually another way of saying the definition of loop, is that those maps are bijections. And so what you do is you look at the group that those things generate. Now, we don't particularly want to favor the left over the right, so we'll take them both, okay? And that's called the multiplication group. And I'll give you an example, which I'm not going to prove. If your original loop is actually a group, its multiplication group is isomorphic to two copies of the group mod a copy of the center. Okay, I'll let you think about why that would be. Multiplication groups turn out to be very useful. They do contain lots and lots of information about loops. There is studying loops through their multiplication groups is a big major industry. And the main reason is because you are changing the study of some non-associative object into studying some associative one that acts on the non-associative object. And that's more familiar. But they don't determine loops. So, for example, if the quaternion and dihedral groups of order 8, they have the same multiplication group. Okay. Now, the main reason I needed that was not because of the multiplication groups themselves, but because I need the set of elements in them that fixes the identity element. This is what's called in loop theory, the inner mapping group. Inner permutation group would have been a better word, but this is just traditional. So this is all of the things in the multiplication group, that group that we just talked about, that fix the identity element. Now, if you start with a group, this is exactly the same thing as the usual inner automorphism group. This is not how it's traditionally defined in a typical abstract algebra or group theory textbook, but it is exactly the same. In general loops, inner mappings are not necessarily automorphisms or anything other than permutations that fix the identity. Okay. Now, what about generators for those things? And this will come up later in some encoding issue. Excuse me, sorry. So the inner mapping group is generated by a very useful set of inner mappings. First of all, there's conjugation. Now that's the conjugation we're all used to. And here I've written it as a composition of left multiplication and the inverse of right multiplication. You multiply by something on the left, you multiply by its inverse on the right, is how we do it in groups. This is the same idea. But in addition, as always, we have non-associativity. So we have other inner mappings than the familiar ones. And these are things that actually measure non-associativity, the failure of these L and R mappings to compose. You would think that L sub x times L sub y, shouldn't that be L sub xy? No, that would mean you have associativity. Okay, so these mappings measure that. These will come up again later in the encodings. Okay, so for example, here's what they would look like in our typical prover 9 files. There's a slightly different convention here, which I'll ignore. So now we have a lot of defined functions. We've got commutators, we've got associators, and we have 3 types of inner mappings. Okay, so there's a lot going on here. And we haven't even written down any actual hypotheses or axioms. We've just defined functions so far. Okay. Let me talk about nilpotency, because this is now the key to actually stating what the AIM conjectures are. So how is nilpotency usually defined in a group theory course? You may not get to it in an introduction to abstract algebra course, but in a more focused group theory course, you might get to it, maybe not immediately, but later. Here's how it's usually defined if you crack open a typical textbook, okay? A group is nilpotent of class n if blah, blah, blah. I'm not even going to read it to you, okay? There's this upper central series. There's some final term, and it's nilpotent of class at most n if that last term coincides with the entire group, okay? Now, if you've taught group theory, you will know immediately that this is extremely difficult for students to wrap their heads around because of the levels of abstraction that are involved in this, the quotients and pre-images of quotients and so on. It takes a long time. Okay, but all that can be expressed equationally. So for example, here is exactly, if you're in a group, not a loop, if you're in a group, here's exactly how you would say that a group is nilpotent of class at most 3. It just says an iterated commutator is equal to 1 all the time. Okay, so this is a first order encoding of a pretty high level thing. Now, how does this work in loops? Same idea, except now we have associators to deal with. Now, this time, instead of showing you class 3, which would be a long list of equations, I'm showing you class at most 2. Okay, so there are 8 equations there. And they are actually I'm cheating because they are the 8 equations I showed you earlier. The 4 that say that commutators are in the center, and the 4 that say that associators are in the center. Okay, so this would be how you say that a loop is nilpotent of class at most 2. Okay, here we go. AIM loops. So here's the motivation. Here's a familiar, easy exercise in beginning group theory. Oh, what time did we start, by the way? I'm sorry. Did we? Okay, so I have to watch time a little more carefully. Which is that the inner automorphism group of a group is, in fact, isomorphic to the group mod at center. Okay, this is often given as an exercise in a first course in abstract algebra. This isn't true in loops. And it's not true in loops for a couple of reasons. First of all, the right-hand side doesn't even have to be associative, so it can't possibly be isomorphic to a group. And secondly, even if it is associative, that still doesn't mean anything. Here's an example of a case where the factor by the center is associative, but that and the inner mapping group turn out to be 2 completely different groups. Okay. So this exercise is senseless in loop theory, but it has a consequence that we could make sense of. The consequence is that of the group exercise is that a group is nilpotent of class at most n if and only if its inner automorphism group is nilpotent of class at most n minus 1. So we could ask, all right, throw away, forget the exercise. What about this? Does this work in loops? Okay. Well, in general, nobody knows the answer. Well, in fact, most of the answer is no, but for interesting reasons. So what we're going to do is we're going to restrict to the easiest case, the case where n equals 2. Okay. And these loops in which this occurs are called AIM loops, which stands for abelian inner mappings. And yes, we just say AIM, like the word. Okay. So a loop is an AIM loop if its inner mapping group is an abelian group. Okay. And so here is the problem. Are these statements equivalent? A loop is nilpotent of class at most 2. So that means that those 8 equations I showed you all hold. And the inner mappings all commute. Are those 2 things equivalent conditions? Okay. This dates back to the early days of loop theory in the 40s. Okay. And Bruck showed one direction in his seminal paper on group theory. And the other direction is the topic here for today. This generated a lot of work, which I won't go into the history of. The best general result is this one from 1994, proven by Niemann, Ma, and Kepka, who proved that every finite AIM loop is nilpotent. but their proof used finiteness in a very essential way. They just assumed there's a minimal counterexample and found a contradiction. There's no upper bound on the nilpotency class. If you know in particular, it could be anything from their proof, as far as is known. And then later, Niemann himself, improved it that every finite loop with nilpotent intermapping group is nilpotent, but again, no relationship between the nilpotency classes. Okay, now the reason that there was a lot of work that suddenly stopped is because there was a counterexample, as it turns out, which often happens in these situations. And this was found by Piroshka Shorga. She found a loop of order 2 to the 7th. Its intermapping group is abelian, but its nilpotency class is 3 instead of 2. And as you all know, if you work in any area of mathematics, when somebody finds a counterexample, that just suddenly, oh, well, I can do that. And everybody starts finding counterexamples. And there were a whole bunch of them just published in succession within the next couple of years after this, including examples in highly structured classes of loops. Although 2 to the 7th is the smallest size still known, which is pretty large. And by loop theory standards, it's pretty large. Okay, so that seemed to be the end of it. And that sounds like, well, that's the end of my talk. There was a counterexample. Okay, but that's not actually where things stopped. So this next part is due to my obstinance. I carefully examined all of the known counterexamples. And I found out that they are actually much more structured than anybody thought. Yes, they were counterexamples to the original conjecture, but they had the property that their factor by their nucleus was an abelian group, and the factor by the center is not an abelian group, but is a group. So, okay, so what would the equational interpretation be? Here again are the 8 equations that characterize for something to be nilpotent of class 2. In all of the known counterexamples, the only one that's false is the first one, the one that has the 2 commutators in it. All of the other ones are true. Now, my philosophy of conjecturing is go big or go home. Okay, so I said, let's just go for it. So I made a conjecture, even though the only evidence was sort of just because a bunch of counterexamples satisfied this. This is called the strong AIM conjecture. Here's the high-level version of it. The high-level version is if you have an AIM loop, so all the intermapping group is abelian, then the factor by the nucleus is an abelian group, and the factor by the center, which is smaller, remember, is just a group. Okay. So equationally, it's saying that the conjecture says in an AIM loop, 7 out of the 8 equations always hold. We know the first one doesn't necessarily hold, but the other 7 always do. Now, just to spoil this, the strong AIM conjecture is still open. Okay. I should have saved that for the end, but I can't do that. I'm not very good at telling jokes either. So punchline first. Okay, now there is a weaker version, and that's why this title of this talk is the AIM Conjectures. The weaker version is that every AIM loop is nilpotent of class at most 3. So there is the explicit bound on nilpotency is 3. Okay, the strong one implies the weak one. I won't explain why in the interests of time, but it's not very difficult to see. And this would improve upon the Niemann-Kepka result if it's true. Spoiler, it's true. Because it doesn't depend on cardinality. It's true even in the infinite case. And we do have this explicit bound. Okay. So let's talk about progress and non-progress. Now this got cut off a little bit because of the fact that I was using a monospaced font. But here is some input. So at the beginning there, you've seen that one before. Those are the definitions of the inner mappings. And here is the assertion that the inner mapping group is an abelian group. what you do is you just say all of those generators commute with each other. And those generators depend on universally quantified variables. So that means that the assertion that the inner mapping group is an abelian group is equational. It's expressed by those 6 equations. Okay. As I remind you, that's a slightly different convention than I was using for defining the mappings earlier. But anyway, it's equivalent. Okay. So those are the hypotheses. We've seen the conclusions. The conclusion, or the goals, rather, I'm sorry. The goals are the 7 identities, the 7 equations that I showed you. Okay. Okay, so great. All we have to do now is turn on prover 9. So let's get our infinite computer with infinite memory, and let's also put it into a time bubble so that a long amount of time elapses for the computer, but only a few seconds elapse for us. Surely this will be easy. Okay. Okay, well, the problem is that this is a very difficult problem, and this is way out of reach for any automated theorem prover, not just prover 9, but any of its competitors, for example. If you just start this, run a job, you will either run out of memory or run out of patience, or both, most likely both. Now, I will say that the strong AIM conjecture has been proven in many, many important classes of loops. I'm not going to list them because they wouldn't mean anything to you. One could argue that all the loops that any loop theorist actually cares about are in such loops, the strong AIM conjecture is actually true. So there's been definite progress, but the general strong AIM conjecture, no, not really. Now, after many, many years of work, and this was, I would say, about 15 years of work, my co-author Bob, who was the one actually running the jobs and using all kinds of techniques to coax prover 9 to do things, was able to reduce the problem to showing that only 2 of the goals are enough. If you can prove 2 of the goals, all 7 of them hold, as it turns out. There are some equivalences here. Those are, there are different pairs you can pick, but this is, say, typically an example. Now, I don't mean just that he let prover 9 run for a long time. This took a lot of actual human work, resetting jobs, changing parameters, guiding the searches, using various specialized techniques that I wish I had time to describe. So this was actual genuine work. He has a lot more patience for this kind of thing than I do. Here's an interesting case where we don't know if the strong AIM conjecture holds, but you would think that we would, because it sounds like it should be an easy case. You remember my earlier diatribe about commutativity? This is it coming back again. We don't know if the strong AIM conjecture is true in commutative loops. Okay. There's only one goal, just show one of the iterated associator expressions is equal to 1. Okay. The progress that we've made on the commutative case is minuscule. It's insignificant compared to every other case. And we don't really know why, other than, as I mentioned, commutativity is just not as strong a property as you might think it is. I'll come back to this toward the end. Okay, well, the weak AIM conjecture is true. We do not have a direct prover 9 proof of this. So it's not like I set up the hypothesis, I set up the goals for being nilpotence of class at most 3. That's a bunch of equations, not just the 7 that I showed you, a bunch of very long ones. Rather, we have a mix of high-level human reasoning based on expertise in loop theory and long prover 9 proofs. Now, I will say that this is an interesting case compared with what's very fashionable nowadays in mathematics, because this proof that we have is mostly formalized. Okay? The parts of it that are human, if there were actually sufficiently robust libraries in current interactive theorem provers like Lean and some of its competitors, the ones that are currently being used a lot nowadays fashionably, it wouldn't be difficult to formalize the human parts, okay, of this. So that's not the issue. The issue isn't to formalize the proof. The issue is actually the opposite. Now, when I've talked about this to loop theorists, of course, I outline the proof, but I ain't going to do that because this is we're getting too long here anyway. But I'm going to skip ahead to some of the consequences of this. The issue is we don't understand many parts of the proof. We have a proof, but there's whole long parts of it which are pure proof-or-nine equation bashing that we have no idea what it's saying. Okay, because it's just a long string of equation with justifications, and the justifications are just plug this part of this equation into this other equation and simplify and things like that. And one can only do so much of that before your head starts to spin. So there's nothing conceptual in those parts of the proof. Now, sometimes when you are dealing with proof-or-nine proofs and using them as I've been doing for my entire career, you run into a situation where you look at an equational proof and because of your own expertise in a particular area, it reminds you of something. And you come up with a conceptual proof of the same thing, that one that's more appealing. This happens all the time, okay? And this is great because that's certainly something that we would prefer. Yes, it's great to have first order proofs to sort of verify that things are true, but if you can come up with a conceptual one that explains something, that's much better. So for example, I gave examples of this already. If you see an iterated commutator equation, then you know on the high level, oh, that means this group is nilpotent of class at most 2. Okay. But as you probably all know from when these things arise, sometimes, okay, so Freud once said a cigar is just a cigar. Well, sometimes an equational proof is just an equational proof. There's nothing you can really do. The equation bashing is just all there is. You can try to simplify it as much as you can, clean it up, but in the end, you just have to live with it. And many projects that I've worked on, both of these things occur. Okay. Sometimes you see, I have a conceptual argument for this thing that I initially used proof-or-nine to prove. Or I have, this is just equational manipulation. I'll just make it look nice. There's nothing else I can do here. Okay. Let me show you why we're not going to the effort of humanizing this proof. Okay. This is one of the technical lemmas. These are the stats from the end of the run. Okay. So the proof took this many seconds, plus some other number of seconds, which is just counting the pre-processing time before the search actually started. The proof has 191,000 steps. Okay, I'll be damned if I'm going to read that proof. Okay. Now, if I were an abusive personality, I would, of course, assign a student to do it. But I'm not. So I'm not going to do that either. Okay. There's no way anyone is going to humanize this proof. Now, yes, there are various techniques that one can use with automated theorem provers to simplify automated proofs, but the scale of the simplification for something that this is large to begin with would be negligible. Maybe reduce it to, 150,000. Gee, that's better. Okay. So the law of diminishing returns says, just leave this alone because there's not much to be gained. What if I went through the years of effort to humanize this proof, which remind you is just a technical lemma, and it turned out that there was no conceptual stuff to it at all. It's just a equation bashing proof, and there's not much you can do.
Can I ask a question?
Yeah.
On that slide? For comparison, do you know anything about the time of the four-color theorem?
Do I know anything about?
How many steps,
Oh, no, actually, I don't.
is this much harder than the four-color theorem or?
Well, in terms of its sheer length, yes. I understand that with later simplifications to the four-color theorem, that its formalization is now reasonably compact.
Right.
Not like, I don't mean like.
Still not human, but.
Right.
Yeah.
Exactly. So let me wrap up because I'm running out of time here. So of course, one of the questions that you would have asked during the question period, which I will now ask for you, is what is my intuition about the strong AIM conjecture, which is still open. I actually think it's false. And this is based mostly on our absolute failure to make any progress in the commutative case. So in fact, my co-authors also agree with me that this is their gut feeling is also that it's false. The problem is that we have zero idea how to even start building a counterexample. Okay, automated theorem proving and such tools are probably not going to help. Finite model builders usually can't make things that of the necessary size. So this would be just some other entirely approach to this, and no clue how to do it. It would be great if it were false. I mean, you might think after being so strongly invested in this conjecture for so many years that I would be deeply disappointed. Far from it. I would actually be very excited if it were false, because that would be an extremely interesting loop. We would probably learn a lot from looking at it. And with that, I'll stop. Thank you very much.
Thank you, Professor King. Different question for this talk.
There was a counterexample at the middle of the talk
Mhm.
to the power of 7.
Mhm.
How did she found that counterexample? Also by computing?
No, no, she's actually very computer averse. So basically, she did it the old-fashioned way. She just basically by accumulating an enormous number of necessary conditions that must be the case if the conjecture were true in the first place. I mean, she had a long, long list. And then she had so many of them that it became clear there's probably a group that breaks them. And so her construction was basically just by an old-fashioned by hand construction of doing some central extensions of two groups until she found a multiplication group of the correct size. And then from the multiplication group, I forget the size, 2 to the something considerably more than 7. And then from that, she was able to construct what the actual loop was. Basically, as soon as she had the multiplication group, she's a pure group theorist. As soon as she had the multiplication group, the correct one, the rest was easy. And then everybody who followed up on what she was doing sort of extracted the essential features of her construction to and then applied it in other special settings, like special types of loops and so on, to try to get the same idea to go. So it was really, I mean, I have to give her full credit. It was really a remarkable achievement, considering that up until just a few months before she found the counterexample, she still thought the conjecture was true. James.
So when you do this human top level stuff plus proof of 9,
Yeah.
are you kind of guessing very strange technical letters and asking for proofs of those, and then you're combining the letters, or how do you find the human parts?
So basically, it's basically it's a series of reductions. So to give you an example, we know that because of a big proof or 9 proof, one that in principle I could probably humanize. So this is one of the shorter ones by the standards of this project. Just to give you an example, we happen to know that if you take one of the goal equations, there it is. Okay, take that second one, and you replace that z with an x. Okay, that actually holds. And it also holds with that same x, y, x associator in all the other possible spots that in the 7 equations. Now that sounds like, okay, so what? That's syntactic nonsense. That actually means something. It means that the quotient by the center of an AIM loop satisfies the equation xyx equals xyx, meaning you can associate xyx either way. That in itself, combined with some other loop theory, tells us some consequences which are actually are equational, but something that are currently out of the reach of Prover 9 or its competitors. So then we can start with those, formulate the next step, run new jobs, and so on. So basically, it was a combination of what the output is actually showing to us and a little bit of knowing how loops work.
So you kind of feel like you might be able to guess that an XYX type thing is a useful thing that could be used 100 times in the proof, but Prover 9 might just discover that randomly on line 3 billion.
Yeah, that's possible. I think in the case of that particular example, Bob Viroff was just trying to see what would happen if you simplified the goals by setting variables equal to each other. So he was just treating it as a formal check to see what would happen. And in that particular case, somewhat to my surprise, he actually got something. But like, just to give you an example, a lot of the proof of the weak AIM conjecture would simplify if one could do this where instead of z being x, y is equal to x. Okay, I won't explain why, but it would turn out that that would make things a lot easier. Still no hope, even in that case, of finding it's true, but still no hope of finding a direct proof. So